you, and we'll check our answers and see how this went. Whenever you have, like here is the thing that tells you to do what we're about to do. If you ever have the limit as x approaches negative infinity or positive infinity like this one, then what we're about to do would be at least one of the things you could do. There are other options, at least one of which we'll look at later on. But for now, it's this one. You want to identify the degree of the denominator, and in this case, that would be 1. So it's x to the first. So degree of the denominator is 1. So we're going to divide every single term in the top and the bottom by x to that degree. So for this one, it would be the limit as x heads towards infinity of 3 over x minus 2x squared over x divided by 3x over x minus 1 over x. We're dividing by x on this one because the degree of the denominator is 1, so we divide by x to the first. All right, we do as much canceling as we can. So limit as x heads towards infinity, and it's 3 over x minus 2x over 3 minus 1 over x. So this will have some pretty similar results to what we had before, but one that's not the same. Some of these terms are going to head towards 0 as you apply the limit. How many?
2.
2, yep, that's right. So this one right here and this one right here, both heading towards 0 as we apply this limit as x goes towards infinity. But the other two doesn't work out that way, does it? So what we get there in the numerator is essentially 0 minus something. Denominator is just 3 minus 0, right? So if I wanted to, I could put equals something over 3 minus 0. But then in the top, if you have negative 2 times some gigantic number, what do you get? A negative gigantic number, right? So, somebody might write this. This is a little shaky on notation here, but I think it's maybe a worthwhile step at this point. And if you have a really gigantic negative number divided by 3, what do you get? Yeah, a really gigantic negative number, right? And so the final answer to this limit would simply be negative infinity. A 3 is not going to do much, because in the time it took us to think about it, infinity just got a billion times bigger, and the 3 didn't really matter. So then the pre-calc trick, so let's review the two that we already talked about. For the pre-calc trick, if the degree of the numerator and denominator are equal, then long-term behavior is what? Yeah, ratio of the lead coefficients. Ratio of the lead coefficients. That was like I think the first one we did. And then one of the other cases is, what if the degree of the numerator is smaller than the degree of the denominator?
0.
Then we're heading towards 0 long term. That's right. And then I don't know if you guys remember this one. In pre-calc, it would have been said, hey, if the degree of the numerator is bigger than the degree of the denominator, what do you do? Do you remember? You had to do like this procedure. Everyone remembers? Division. You actually do long division, or you maybe could do synthetic division depending on what the degrees and what the different top and bottom are. In this case, you do long division probably, be the way to go. And so you think, okay, long division would yield a diagonal asymptote usually. But did you know you can actually have a parabolic asymptote? Or a cubic asymptote if the degrees are different by more than 1? So you're going to have like some really funky asymptote, right, for sure, whether it's just a linear, diagonal, whatever. But you're going to be looking at long-term behavior of going way up or way down probably. And so this one is way down, negative infinity. Well, anyways. I will be showing you in the second semester, I will be showing you a different technique you could use for questions like these. Okay. Any questions, concerns? We're going to get a little more repetition here with a couple other situations, but otherwise, we good? Okay, awesome. So then number 4 might look a little bit out of place. I mean, you might look at number 4 and think to yourself, wow, this looks very much like a pre-calc question, doesn't it? Determine the horizontal asymptotes for that. And I agree, it is sort of a pre-calc-ish kind of question, but we can now approach it from a calculus perspective. When I say horizontal asymptotes, I am talking about what's happening on the way far right edge of the graph, or maybe the way far left edge of the graph. When I say far right edge or far left edge, what am I really talking about? Yeah, plus or minus infinity. So if I want to find the horizontal asymptotes, what I've got to do is say, all right, if I want to see what's going on the far right edge of the graph, I need to do the limit as x approaches positive infinity of 2x squared over x squared plus 4. And if I want to see what's happening on the far left edge of the graph, I need to do the limit as x approaches negative infinity of 2x squared over x squared plus 4. A lot of times the behavior on the far right edge and the far left edge is the same. Sometimes the behavior is very different. It just kind of depends on the nature of the graph of that particular function. So if you guys would, take a minute. Let's see if you can figure out what the far right behavior would be. So the horizontal asymptote heading right, or the far left behavior, horizontal asymptote heading left. So again, that setup should look pretty familiar. We've done 3 of them so far. See how it goes for you. I'm hearing like a 2 with kind of a question mark at the end a little bit, right?
I think it's
2? Maybe?
2.
2? More confident?
2.
All right, 2. So the answer is 2. What makes this one, partially what makes this one what it is that all the degrees are even.
The trick.
Say again?
The trick.
The trick. Yeah, but the trick, so the trick, depending on degree, I think the trick will mostly work, but if the degrees are even and odd, or odd and even, or odd, odd, or even, depending on what the function actually is, can make a difference. So, anyways. Question?
So, what is different from infinity and negative infinity?
In this one,
Yeah.
not much. So like if we graphed this,
Yeah.
I am fairly certain, let's see here. I'm fairly certain this graph would look, feel free to check me on this, I think it's going to look about like that. Somebody feel free to check me. I am... No. Yeah. I think that's what, and 2 would be, well, I'm really asking, will someone grab a calculator? Use your fingers and the buttons and double check me. Pretty sure that's what it looks like. So in other words, what I'm thinking is as you head to the far right edge of the graph, you're approaching a horizontal asymptote of 2. Far left edge, same thing.
And then when you're working out the problem, is there anything that could make the answer different from the infinity answer to the negative infinity answer?
Yeah. So there are plenty of graphs in which the left and the right hand behavior are different. So an example would be arctangent. Arctangent looks like this. So for arctangent, the far left edge of the graph, the horizontal asymptote is negative pi over 2. Far right edge of the graph, it's positive pi over 2. And so there are certainly plenty of situations where that is the case. I would say, in my experience, typically if we have like the more standard rational graph like this, probably you're going to get the same behavior both directions, unless you've got the degree of the top bigger than the degree of the bottom, then you're going to get one of those diagonal asymptotes, and then one would probably be positive infinity, the other one would be negative infinity. The easiest way to do it is to actually check it and like divide through by degree and see what actually happens and go with it from there. That's the easiest way to do it. In this case, I think you got 2 either way. Yeah.
Can you explain like why 4x over x squared, or just any number over x squared, is always equal to like 0 when you simplify it?
Have you watched the video yet?
Yeah. Just trying to figure out.
Okay.
Recap, I guess.
I'll do this quick.
Yeah.
So here's the deal. And it's not just x squared, it's anything over x squared, x cubed, x to the 4th, x to the 5th. So I'll make a table. So this is not directly connected to what we just did. So if I've got x, and let's say what you said, say 1 over x squared, and this is called f of x. If I say the limit as x approaches infinity of f of x, right? Let's think about what happens. I'm just going to make a table. And remember, a limit is about long-term behavior. Like, what is the pattern? It's not what is the value of what's the y value of the graph at that point? Because we're talking about infinity, especially here, right? It's what's the pattern. So I want to head towards infinity. So I'm just going to go 1, 10, 100, 1,000, and then I'll go like 10,000, and then how about 1,000,000? And then how about 1,000,000,000? Let's think about what the outputs would be doing. So if I plug in a 1, so would you agree with me that I am heading towards infinity with my inputs?
Yeah.
Okay. So then as I plug in, what's the output for 1?
1.
And for 10?
100.
For 100?
And then 1, yeah, 1,000 or
10,000.
10,000.
And then 1,000,
1 million.
1 million. And then 10,000, 1 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And this kind of is making my point here, isn't it?
Yeah, it just gets bigger.
And so this would be 1 over 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. So as the input gets really, really huge, do you see how the fraction is getting closer and closer to 0? Right? Because like 1 over whatever that huge number would be for the last little section there,
Also, it approaches 0, and that's why it's, yeah.
the limit would be 0, right? And so we're not saying that the graph actually hits a 0 y value. We're saying that the pattern is heading towards 0.
Right, yeah, that makes sense.
Okay. All right. Any other questions? Okay, awesome. Well, you guys take a look at numbers 5 and 6, and I think for you guys to handle numbers 5 and 6, you probably should refer back to the rankings that you saw in the intro video. I think that's going to be your best help. As I mentioned earlier, there's going to be some different techniques I'll teach you guys later on, but for now I think the rankings thing would be your best bet. So use those to help you try to figure out what 5 and 6 would end up being. So for a question like 5 and 6, how much work am I expecting that you would show? It's a fair question, right? At this stage of the game, if you had a question like 5 or 6 on a quiz, I really wouldn't be expecting you to show any work at all. I would be expecting that you would understand the relationship between the relative growth rates, like the rankings thing, but that's about it right now. Later on, I'm going to show you a more well-developed technique on how you would deal with something like this. I'm just trying to, I don't know, preview is the wrong word, but just kind of lay some foundational stuff for when we do get to that. You'll be able to remember this a little bit instead of like it being this completely foreign, like right turn into right field. And you're like, whoa, I never saw that coming. We can refer back to this, be a little bit easier, hopefully. Okay, so for number 5, just shout it out. What did you get? 0 is right for number 5. For number 6, what'd you get? Infinity. And here's the reasoning right now. And again, if this feels a little shaky, I get it, and I'm okay with that. I get it. It is shaky. So in number 5, the numerator will eventually grow infinitely slower, I guess, if you could say it. It'd probably be better to say that the denominator will eventually grow infinitely faster than the numerator. So the growth in the denominator will outstrip the growth in the numerator, therefore it would be heading towards 0. The reverse is true, of course, in number 6. Number 6, the numerator is the faster growing function eventually. So eventually that numerator will completely overpower the denominator. We'll be heading towards a non-existent or an infinity answer. Question?
How do you know that the numerator is going to grow slower than the denominator?
So here, this is a polynomial.
Yeah.
And here, this is an exponential.
Mm-hmm.
And if you want to take some time to prove this to yourself, that's fine. I'm not going to do it here in class. We could use a calculator and show that eventually any polynomial that you can dream up versus any exponential that you could dream up, the exponential will eventually grow infinitely faster than the polynomial. And then here, it's the exact reverse. You've got an exponential in the top, and you've got a polynomial in the bottom. And so once again, the exponential will eventually grow infinitely faster. And so since the top is the one that's going to grow infinitely faster eventually, that's where we're heading towards infinity.
Is number 4 a polynomial?
Yeah, x to the a. So a would be like a number, like 2, 3, 5, 10, whatever. Where x would be the variable. And if you notice for the exponential, the base is a and the exponent is a variable. You good?
Yeah.
Okay. Any other questions? Dan?
Yeah. Are these the only rankings that we really need to use that are going to be relevant for these kind of questions? Okay.
And in fact, it's probably beyond where you need to be. Numbers 1 and 2, I don't think we'll deal with much, if at all, in our class.
Cool.
If you ever took a Calc 2 class, you would deal with both of those. I just thought I'd give you the whole list, but we really only deal with 3, 4, 5. Okay. Anybody else? Question, concern, comment? Okay, cool. So, what remains for us today is actually some stuff we've been practicing, and we've practiced this already, and here it is. It's called optimization. So you think about the word optimization, you might think to yourself, what on earth does that mean? Got a few fill in the blanks here. I thought we'd fill them in just to help us remember a little bit about what this is. I think we'll probably just do one or two examples today. We'll stop probably well short of the end of our class. We'll do something different at the end. And then we'll save the other couple, maybe two of them for next week. And we'll be kind of rapidly wrapping up this particular chapter at this point. So anyways, let's see if you guys can figure out what goes in these blanks. It might be a little vague. It's purposely like that. See if you can figure it out. So optimization is finding an optimum value, also known as finding a blank or blank. Max or min. So we've done this already, so this is good. And then maybe this next phrasing will look really familiar because I know I've said this, it feels like 1,000 times. Maybe it's more like 700. Feels like 1,000. I don't know. Blank and blank occur at blank or blank. Any ideas? It's very generic. Yeah, but I'm hoping that you've heard me say this enough. I'm exaggerating when I say 1,000, but if I say 30 times, I'm not exaggerating. I probably said this 30 times in the last 2.5 weeks. Blank and blank occur at blank or blank. Oh, okay, and what would you say the first ones would be?
Absolute and max.
Okay, yeah. So I'm not going to put the word absolute in there yet. I'm just going to say min and max, and then I heard somebody say endpoints or critical numbers, right? I've asked you guys, what are the candidates for relative extrema, candidates for absolute extrema? Lots of times. That's what that's getting at. And if you didn't know what the blanks were, it's okay. It's not really a quiz. I just wanted to see if you'd heard it enough, and maybe you haven't. So you're hearing it again, and I'll keep asking. So min and max endpoints are critical numbers, and blank blank are places where the derivative is blank or does not exist. Critical numbers, there you go. Critical numbers are places where the derivative is blank or does not exist. That's right. Okay. So if you know that, you'll at least have a place to start on all these. And I'm not saying that makes these easy, but at least you'll have somewhere to start. Make sense? So what this is, essentially, optimization, is it's all about maxes and mins again. But it's all going to be in the context of a situation, a.k.a. a word problem. That makes sense? And so I just have I put here steps, but steps maybe is too strong of a word. These would all be like suggested strategies because not every single one of these steps is going to apply to every single question we might look at. So, number one, maybe you draw a picture or a diagram. And I literally mean that. Sometimes that's going to make absolutely no sense. Other times it'll make a lot of sense. Number two, this one we're going to always do. We need to figure out what is trying to be optimized. And maybe we write an equation for it, or maybe we have something else to kind of describe what's going on. But we're going to have some kind of an equation to help us, right? Okay. Typically is too strong. I'd say sometimes we have to reduce the number of variables. So we might have to write a secondary equation to reduce the number of variables from too many to just right. I think sometimes the realistic domain is pretty important. For instance, you can't have negative 30 feet of fence. You also can't use 0 feet of fence and actually enclose anything, right? So there's some realistic domains to be considered. And then number 5 is the most loaded. You can kind of snicker, I do. It says, use calculus to determine the max or min. Wow. Right, that's like a pretty loaded statement in the sense of, whoa, just to say, use calculus. There's a lot involved there, right? There's a whole lot of stuff involved. You got to consider, are the endpoints going to matter? And I'll just tell you right now, at this point, hey, Addie, are you going to be done with that soon? Kind of been doing that the whole class. I want to be respectful, but that's not. So you'll find that in this part of class, in Chapter 3, we're not going to consider endpoints for these a whole lot. We might think about them and discuss them, but it's not going to be that big of a deal. When we get into Chapter 4, later on, the endpoints will be a much bigger deal, and they'll come into play a lot. So I wanted to reflect real quick on what I mean by use calculus, and I want to show you something in your notes that maybe you haven't seen, I know a couple of you have. If you guys would, flip all the way through all these optimization questions and flip through this little thing on 3.9 and get to the end where it says extra resources. And these extra resources are basically various forms of a summary of the whole chapter. And I thought I would direct you guys to this blue boxy flowchart. Keep going there. It's the last one, I think. You can look up there too. I know the writing is pretty tiny, but if you got it in front of you, you can see it. It should look, keep going there, Stan. I think it's one more page. So I've had a fair number of folks that said, talked to me in the last week or so, and they've had this question. Hey, I don't understand when I'm supposed to use the first derivative to do this or that, or I don't know when I'm supposed to use the second derivative to do this or that. And the honest truth is, most of the time, the answer is you can use whichever one you want, which I know is a little disconcerting because you want to hear me say, no, you always use this here, and you always use that there. And the truth is, any rules that I make up like that would just be purely made up by me and might actually be more misleading than anything else. I'm just here to tell you, if you're looking for a max or a min, there are going to be times when you have to use the first derivative, times when you have to use the second derivative, or times when you have an option, depending on what it is you're given, what you're trying to find, and how easy or difficult it is to work with the things you've been given. So I thought I'd show you this little flow chart here. Like, this is the use calculus part. So check this out. It says directions. Like, this is the thing you've been asked to do. Find relative min or max. So your first step is to find f prime. So finding f prime might be complicated. You might have to do some derivatives to find it. It might be simple, whereas you just say, like, you gave it to me. It's right there. Or you might have to find a net rate. Yeah? Rate in minus rate out. Water tank question. Air conditioner question. Right? Rate in minus rate out. So you got to find f prime. And again, that has a varying degree of difficulty. Just depends on what you're given. Once you have found f prime, you don't have a choice here. You need to find critical numbers, and that's places where f prime doesn't exist or is 0. Here's where you get a choice. You think to yourself, I found my critical numbers. Do I want to use that, or do I want to use that? So I can test the critical numbers with either the first derivative test or the second derivative test. You can see that's where it branches out. So if you were to say, hey, if I'm finding relative extrema, do I have to use the first derivative test? Do I have to use the second derivative test? Or when do I use this? When do I use that? It's a choice. It's a choice. Remember how I described these two tests? One of them is like a power saw, and the other one is like a hand saw, right? They both have the same general purpose, but they go about it pretty differently, right? You'd use a power saw in a lot of applications, but if you're trying to do some delicate work with something you've created, maybe you'd use a little hand saw, right? If you're trying to, saw down a tree, maybe you use a chainsaw, a third tool for the job. Does that make sense? So different tools have different purposes, and so these two tools have their own purposes. And then what is the first derivative test? What is the second derivative test? You can see those outlined here. And you notice that one arrow diagonaling back up, that's if f double prime doesn't tell us what we want to know. It's silent, right? That's when f double prime equals 0. That means you've got to go back and use the first derivative test. Might happen, might not. Just depends. When do you pick what you want to pick? Hopefully you can answer this one. Why would I choose to use the second derivative test instead of the first derivative test? What would be, say again?
When it's easier.
When it's easier to do what?
Take the second derivative.
Yeah, when it's easy to find the second derivative. If you look at that second derivative, you're like, oh man, that's going to take me 10 minutes. You probably just ought to use the first derivative test. But if you look at that and you say, you know what, I could find that second derivative in like 3 seconds, it probably, again, in my opinion, would probably be better to use the second derivative test. It's a little bit easier to use in that case, I think. Again, this is a matter of opinion. I have my reasons, and you may or may not agree with me. I just wanted to share kind of the answer to the why would I use this instead of that. Okay, so it makes sense? Okay, I hope you have fun with these examples. I know I do. These are all like pretty real world-ish, and I thought we'd start with number 1. So here we go. Please feel free to read this. I'll read it out loud. Remember, the first time we approach one of these story questions, we don't get hung up on, the rate of this and x plus 5 and all these details. We just read it like a story. So I'll read it out loud. The concert is beginning soon and people are starting to get in line. The rate at which people join the line is given by J of T, measured in people per minute. The rate at which people leave the line and enter the concert is 7 people per minute. For T greater than or equal to 0, when is the line shortest? You're going to find later on it's a pretty sad thing, like the line at one point or another just keeps getting longer and longer, and people just are not going to be getting into the concert. Kind of sad, but whatever. Maybe it was a free concert and they only have so many seats or something, right? That's happened before. Okay, so I read it out loud. Can anybody summarize this in just like a handful of words? Who?
People are getting in line and leaving the line.
Yeah, people are getting in line and leaving the line. Fair enough, right? Okay, so it might be wise for us to identify any rates that are going to play into this. And the objective is pretty clear. You know, when is the line the shortest? We're going to be trying to find this. When I say when is the line the shortest, what kind of an optimization am I talking about? A minimum. So we want to think of like the minimum line length. We're trying to mark this question up a little bit like we've done with other word problems. So we're trying to find the minimum line length. Just kind of file that one away. Let's think about these rates that might play into this. Do you see any rates that would affect the length of the line? Yeah, people per minute is a big hint, right? Do you guys see what he's talking about? Which one are you talking about? I see 2 of them.
Yeah, there's 2 of them.
There's 2, yeah.
T and when people are entering the concert.
Yep. So J of T is the rate of people joining the line. That's why I picked the letter J. And then the rate that people leave the line is 7 people per minute. So I'm going to have you guys do something here in a second, but I just want to remind you of something. I think you probably see this. Is this not a water tank? Like, to go back to that original kind of type that we looked at of these, you've got a rate causing the line to get longer, and you've got another rate causing the line to get shorter. Okay? So what I would like for you guys to do is take a minute and think about how these 2 rates are going to interact to form our net rate. Make sense? So think about how, like, I want you to write it down. I want you to write down on your paper the net rate. I don't want you to think about it only. I don't want you to talk about it only. I want you to do both of those and also write it down. Okay? So think about what the net rate would involve, because we got 2 rates kind of going against each other, right? One rate making the line get longer, one's making the line get shorter. How are they going to interact?
Do you want to choose a function for you?
Do I want to choose a function for you?
The letter? Yeah, what letter do you want me to use?
So if you wanted to, like, we could go there. We could say L stands for length of line. Thanks. Have a good day, Judy.
Would this work?
No.
Which one?
It's fairly close. It's fairly close.
Is this correct, or should I
Hang on
not
one second.
write T?
Hang on one second. It is asking for the shortest length of the line. So it's asking for like the smallest amount, more or less, right? And I've given you rates.
Isn't this giving like the rate at that point?
This is not giving me the rate of anything right now. No, you've made a little mistake. Like, you're fairly close, but you've made a little mistake. I know what this is. I know what that is. I have no idea what C is.
That's my equation.
So you want to, if you're going to introduce some brand new variable or name or something, you need to define what that means for me.
C is the length of line.
There you go. If you put that in there, now I think we're in good shape. You're welcome to make stuff up like that. Just tell me what it means. Go ahead.
So this would be, I was thinking of like the air conditioning one, right?
Yeah,
So
totally.
entering the amount entering, the rate of the amount entering minus the rate of the amount leaving.
Sure.
Okay, so
Yeah.
does T stand for time?
T stands for time.
Okay, so where's like my other value here? Or
The other value?
I don't know, I feel like there would have to be like an X variable standing for the amount of people. I feel like
You can if you want. So like Jake was saying, hey, what could I use for another variable? And he, like, I think said L, right? So he said, hey, L would stand for this.
Right.
Like, you can do it that way. There is no
But
requirement
is
that you
just
have to
a
do it
lot
that way.
harder?
I don't think so.
Okay.
I
So
don't
could
think
I
so.
put, so for my other rate, I would do, so I'd set this up as 2ln, I'd just put my first rate and then I'd do minus 7t.
Some other folks have made the same mistake.
Okay.
No T.
No t.
No.
Just
We'll
7.
talk about that. Yep.
Oh, are we gonna talk about why there's no T?
Oh, absolutely.
And
we
then,
will.
are we also allowed to use a calculator?
This one, I think so. Yep, definitely. Kayvon, what do you got, bud?
Okay, so
I think we would definitely use a
work through
calculator on
this.
this one.
We would.
You're barking up the wrong tree with this ln of blank stuff,
Yeah,
and
that's why.
I would not expect you to do that without a calculator.
Okay.
Yeah.
So like,
I like your setup. Like you have the 0 equals thing up there towards the top. That looks real good.
so just like plug this into a calculator and graph it and look at. Okay.
Yes, please.
So I have a question. I don't know if this is right, Max, and we're just talking about this, but for 7 people per minute, do we need T at the end of that? Because
Yeah, we're going to talk about that in a second. The answer is no.
no.
We do not want that there.
So I have a question.
I understand why you would put it there, and I don't blame you for it, but
What I don't understand is that it gives us -10 back, but when I put it back in, it gave us a non-real answer. And so,
yeah, because you can't do, like if you plug that back in, you'd get
Yeah.
ln of -9.
so there's no answer then.
There should be. Don't do it that way. Do it on a graph. I'm not sure even what that is. That's
I did math.
no. I don't even. I don't think that's doing the thing
I
that
did
you.
the solver here.
Ugh,
We'll do it.
something's
that not-
messed up. That I would just use a graph.
Okay.
Have you used the graph before?
Yeah.
Just use the graph. Looks better. So guys, is it a check to see if you got it right?
No, I just want to make sure my equations.
Yeah. Check to see if your equation is right. Let me show you. Can I show everybody right now? Okay. Hey guys, check this out. I have seen a couple of really good things, a couple of really close things. Please, hey guys, listen. Really bear down right here. Press in and listen and ask a question if I say something that doesn't make sense. Okay? So here would be one thing that could be done. I've got a rate causing the line to get longer, and it's 2 natural log of t plus 1. And I have a rate causing the line to get shorter, and that is 7, right? And so I would say that my net rate is 2 natural log of t plus 1 minus 7. Now, well, we're going to talk about, there's one additional thing we need to talk about that, but let's talk about another thing first. If you wanted to say this, if you wanted to say like L of t is equal to the length of the line, you are welcome to do that. And this is totally optional. There is no requirement that you do something like this. If you wanted to, you could simply use this, and that would be totally fine. But if you wanted to say that L of t is the length of the line, then what would my net rate equal? It would not equal L, because L is the length of line, and those two things are not lengths of lines, they are rates. And so what's the rate of change of the length of the line? L prime. It would have to be L prime. So if you were setting it up this way, you would have to write L prime equals. I'm not saying that you have to do that. In fact, I'm not going to do that here. I'll just get rid of this entirely. Question though, Sam?
Why is it not 7?
Yeah, we'll get there. We'll get there in a second. That's the last little piece I want to get to. I just want to make sure that we're good. Are you guys okay with the fact that you could say L prime equals the net rate, or you could just have the net rate? Either way. Let's talk about the thing you want to talk about. And can I be so sorry?
Because it's per minute, so you don't.
Hold, slow down. So let me talk about this. This has been for sure the most commonly asked about thing. Should there be a t multiplied by the 7, right? So I blame this on one person only, and it's not you. I blame this on whoever you had for middle school math or maybe Algebra 1. And here's the deal. In Algebra 1, weren't you trained, I mean like trained hardcore, that whenever you have a rate, you immediately multiply it by a time. Distance equals rate times time. I mean, like, honestly, if the car was going 30 miles an hour, don't you just like instantly go 30t? Right? Can we talk about why that is incorrect here? I think it has to do with concepts and units. We as you guys, I'm sure, are well versed in this at this point in the class. We don't just do stuff because we always do stuff. There's a reason for doing what we're doing. Let's talk about the reasoning for this. What are the units for 2 ln of t plus 1? Come on, what are the units? It's going to answer your question. Those of you that really wanted to put a t there, what are they? People per minute. People per minute. Okay, that's a rate, right? What are the rates? What are the units for the 7? People per minute. So as this currently stands, as written, this is beautiful. It is a rate minus a rate. It makes perfect sense. However, if I put this in and say, you know what, I learned from middle school, I learned from Algebra 1 that I always multiply a rate times a time, and I go times t, let's think about what that does to the units. What are the units on the t? Minutes, right? It's time. So times minutes, what does that do to the units? People per minute, which is a rate, minus people, which is an amount. A rate minus an amount makes no sense. Imagine, what if you got pulled over by a police officer and you were going 80 miles per hour. He caught you for 80 miles per hour and he says, listen carefully to my words. I caught you at 80 miles per hour. I need you to go 15 miles slower. That makes no sense. I wouldn't recommend that you critique the officer's statement at that point. If he said, I caught you going 80 miles per hour, I need you to go 15 miles per hour slower, that actually makes sense. Please don't correct him if he says it wrong, because you'll probably get a worse ticket, but you don't want to make him mad. But do you see why that's ridiculous? For me to say, hey, I've got some people per minute, and I'm going to subtract a number of people from, wow, what? That makes no sense. A rate minus a rate makes sense. An amount minus an amount makes sense, but a rate minus an amount makes no sense. Now, let me challenge you on one more thing. Why were you, and I say this tongue-in-cheek, why were we so interested in multiplying the 7 times a t and not the 2 ln of t plus 1 times a t? They're both rates. Why were we not insisting that we needed to go times t? Because wouldn't that at least be consistent? If you have a rate and you want to multiply it by a time, okay, shouldn't you multiply all the rates by times? Isn't it because the 7 is a constant? Don't we kind of feel like, hey, there better be a variable in there because if there's not, something is seriously wrong? This is where thinking and rationalization is huge. Instead of you know what, we always do it this way, so I will be doing it that way. Don't think that way. Take it for what it's worth, okay? This is a really common issue. People want to take a constant rate, whatever it is, whether it's 7 or 20 or -3, and they always want to multiply it by a t or an x or whatever because they're just uncomfortable with a constant rate. Have I answered the question? Maybe it was a longer answer than you anticipated, but do you get it? Okay, so let me get rid of these t's because they don't belong. Yes, sir.
On the 3.1 to 3.3 practice, there was one of the questions that you put a t after.
Let's not go there. I would like. Do you understand why I would like to finish this one before we rabbit trail off to something else? I will say this. It was a slightly awkwardly worded question, but the word each was a key piece of that question. But I don't want to derail this and go to that and come back to this. Okay. All right. So let's talk a little bit about 3.1 to 3.3. Remember, what's our goal here? What's our end game? We want to find the minimum. Okay? The way that you find the minimum of the length of the line, listen carefully, is to set the rate of change of the length of the line equal to 0 or does not exist. Have we not just found the rate of change of the length of the line? So what I'm going to do is consider the DNE here. There is a feasible DNE. What would cause this to not exist? If the t was -1 or less, right? If the t was -1 or less, and notice how that does not apply because we were told that we're only going to be dealing with non-negative times. right? So I say all that to say we could ignore the DNE safely. But I am going to set this equal to 0. And as I walked around, there were a lot of folks that were trying to solve this. I didn't make it clear here. This would definitely be a calculator active question. So I'm asking those of you, which is most of you that have your calculators out, take a minute and do this. Graph it and solve it, right? Graph it and find the x-intercepts. Please practice that. Some people seemingly are quite rusty at this. Please take a minute, graph it, and let's solve it, okay? Graph and solve using the x-intercept or the zero finder is what it is.
Charge my computer before it dies on me.
Good idea, good idea. Anybody have an answer for this one? Go ahead, Luke.
32.1.
Hey, remember we always do 3 decimals. That is the habit we are in. 32 point what?
115.
32.115. You guys agree with that?
Yes.
Okay. So t equals 32.115. What is that in the context of this question? It's a critical number. It's a critical number. And it might be when we have a minimum or a maximum, right? So we need to confirm for certain that this generates either a minimum or a maximum. And this is where I get a choice. And this is where you get to think about this. You think it would be good to try to use the second derivative test? Or should we use the first derivative test?
First.
Why?
Because the second derivative would
suck.
Second derivative is really not that hard, but we don't even know how to find it yet, to be honest. We don't know how to differentiate natural log. It's really honestly not that hard, but we don't even know how to do it yet. What's another compelling reason to use the first derivative test instead of the second derivative test? We got a graph of it right there in front of you, don't you? There's a graph on your calculator that you just used to find that 32 point whatever number, and it's right there. So let's use it, right? Let's use that graph. So what is going on with the net rate at that critical number?
It's a minimum.
Yeah, it's where the rate of change, the net rate goes from negative to positive, creating a minimum, right? So I can now, based on what I've got on my calculator, the data there, I can say that the length of the line is minimized when t equals 32.115 because I guess I've already shown that 32.115 is a critical number, so I can say because 2 ln of t plus 1 minus 7 changes from negative to positive. At that critical number. So this would be on the back end, like if you decided to use like an L or an L prime or something like that on the front end, the wording on this would be a little bit easier on the back end, right? Because you could say, hey, you know, L is minimized because L prime changed from negative to positive. So again, your choice on if you wanted to do something like that. No. In fact, anytime you write a sign chart, I'll ignore it for the most part. I'm going to, like, if you got to give data. So here's the thing. If you want to supply some numbers that prove the whole negative to positive pattern, you are welcome to it. I know that you have a calculator in front of you, and I'm assuming you probably graphed it to solve that equation. Therefore, I'm assuming that the graph is right in front of you, and I'm also assuming that you know what that graph means in terms of mins and maxes. So if you think what I just said, I'm assuming a lot. And if you can navigate that correctly, I feel pretty confident you know what you're doing. Now, if the calculator is not active, that means a couple of things. It means the numbers would be a lot easier, and it also means you'd have to supply some evidence, right? Because if you don't supply some evidence, I can't think to myself, well, I bet you they graphed it on their calculator because you didn't have the calculator. And I'm going to have to say, all right, well, I need to see where they supplied some values to support their whole negative to positive routine. So if there's a no calculator, you probably have to supply some values. Here, not too worried about it. Good question. Other questions? What can I do to help you?
Is there another way to word it compared to the length is minimized?
Sure. So if you said, if you wanted to use this, and you said, all right, well, this is L prime, then what you could do is this. You could say, I'll do it like this. You could say L of t is minimized when t equals 32.115 because L prime of t changes from negative to positive at 32.115. So that's slightly easier wording, I would say. Okay, any questions? Hurry back, Sam. Hurry back. Okay. Seriously, any questions? Okay, cool. So as you guys can see, this leaves us with 3 examples. And I just want to skim through these really quick. We won't do these until, I guess for you guys it'd be Tuesday, wouldn't it? Yeah. So let's just skim through these just so you kind of know what's coming up. Example 2, this is actually a revisiting of the water tank question. We'll probably save this one for the last one. Not because it's most difficult, I just want to get a little bit of space between the water tank type questions. Number 3 is an example that involves flow rate of traffic on a road. Again, I hope you can see why that would be highly practical, why someone would consider trying to maximize the flow rate on a highway. Okay, and then number 4 is one of my favorites. I think number 4 is probably what we will open with on Tuesday morning. It has to do with something that a lot of people don't even consider, that if you have a fixed amount of fencing, the shape as well as the dimensions of the way that you arrange that fencing will provide different amounts of area enclosed within that fence. So we're going to kind of investigate that a little bit as well. Sorry, what? So you can do it without calculus, but you just got to use your little calculator max min finder. We're going to do like the real thing. That's all it is. So did he do like a box where you fold the flaps up, or was it a farmer's field? Yeah. So we're going to do the calculus behind what your calculator's doing. Hey, so what I thought I would do here for you guys, listen up please.